Hi and welcome to Lesson 4 of Dynamics in Space for Higher Physics. This lesson is all about motion time graphs. It's the second lesson in motion time graphs and it's going to be about displacement time graphs. Okay, a quick starter task here, and you may wish to use your pause button in a couple of seconds. But from this velocity time graph, can you calculate the acceleration during the first 2 seconds? And can you calculate the displacement after 3 seconds? It'll move on to the next slide in a couple of seconds, so if you wish to try this yourselves, please pause now. Okay, so the solution to this. Well, the first question was asking about calculating the acceleration during the first 2 seconds. Okay, so the first 2 seconds are from here to here. 2 seconds along here and 2 seconds up to this point here. There are 2 ways of doing this. You can either use the equation that you used last year, and I'm afraid unfortunately my animation doesn't easily allow me to show you this bit by bit, which is a equals v minus u over t, remembering that v is the final velocity, so the final velocity v here is read off the axis here after 2 seconds, it's 1, and the initial velocity u is negative 1. Putting this into the formula, 1 minus 1, and then dividing it by the time, so it's the 2 seconds, the time to accelerate, 2 seconds here, gives us an answer of 1 meters per second squared. I'm not going to go over this in any more detail at the moment, because this is something that we've covered in the last lesson, and we've also covered it extensively last year. If you're not sure about this, go back to Scholar and check out there. The second method, and it's essentially the same thing, is by using the gradient, using the fact that the acceleration is a gradient. That's really what we're doing in the formula above too, but in this case we annotate it slightly differently. So we're looking at the difference in the y's over the difference in the x's. This is again something you should have done in maths. The 2 points that we're looking at here are going to be a final point, an x2, y2 of 2, 1 coordinates, and an initial point of 0, negative 1. Again, putting these coordinates into here, the difference in the y's, you've got to make sure you get them the right way around. It's 1 minus 1, same as we had above. And then the difference in the x's is 2 minus 0. 2 seconds take away 0 seconds. And again, that gives you the same answer. The reason I'm pointing this out is because the gradient method is really one that we're going to be using most often at higher. Okay, the second question that you're being asked here was to calculate the displacement after 3 seconds. Now we can use the formula that we used last year, that the displacement was the area under the graph. The reason that under is in apostrophes here is because it doesn't, strictly speaking, apply in this case. I'll make it clear in a wee second. Right, in this case we've got negative and positive areas. So down below the x-axis, this is a negative area. And the area above the x-axis here is a positive area. This area isn't strictly under the graph, this is really more above the graph, but instead of under, if you kind of read between the graph and the axis. Okay, these are our 3 areas. The kind of browny area here, area 1, is a negative area, and the red and the blue areas here are positive areas. Now I've split these up into 2 up here, the same as you would have done at National 5, just to make it a little bit easier to calculate. In the calculation, the brown area ends up being negative 0.5 meters, which really all that means is it's going it's moving 0.5 meters in one direction. And it'll be in the opposite direction to what it's doing from 1 to 3 seconds. Right? That's all it really means. So negative 5 plus 0.5 plus 1 gives a total of 1 meter displacement. Today's learning intention is that we're going to learn to interpret displacement time graphs. Remember, displacement, the letter is S, so we'll call them ST graphs. The success criteria are below. Okay, I put this warning in just in case someone wasn't watching the video, but there are lots of graphs in the following slides. They can get a wee bit overwhelming, and they do begin to look a little bit similar. I would take your time to go over this. This is not something you can read through and do in a oneer. It's really important that you try to read and understand each graph and understand each worked example that I'm going to show you. It does take a lot longer to do this, and it possibly is something you won't do over one lesson. It might take 2 or 3 sittings, but if you can truly understand this the first time round, then it's going to make things an awful lot easier later on. If you don't understand it, please make sure, by the way, this is the video that goes with the presentation, but please make sure that you pause, replay, go back, make yourself some notes, use Scholar, and most importantly, come and ask. Ask us for help on the Google Classroom. It's really important that you do that, because I don't want you just to move on if you don't understand what's going on here. First of all, a little bit of revision. You should have covered some of this stuff at National 5 last year, and in the last topic, equations of motion at higher, we've certainly covered some of the concepts here. Okay, but it might be new to you. A displacement time graph tells you the position of an object at any time. So on the right hand side here, I've given you an example displacement time graph, and the numbers on there tell you a couple of things. First of all, they tell you how far the object is away from the starting position, but the other thing that they show you is through the negatives and positives here, it tells you what direction the object is, or what side of the starting position it is. Because displacement's a vector, these positives and negatives can tell you whether it's one side or the other side of the starting position. So to explain this to you maybe a wee bit more clearly, imagine that we have our positive values here on the graph, meaning to the right, and our negative values here, meaning to the left. What that means is that for the first 3.3 seconds or so, because the values are all positive, these are all positive values, they're all above the x-axis, that means that the object is situated to the right of the starting position. From about 3.3 seconds to 4 seconds, the values of displacement are all negative. So that means it's situated to the right. At this point here, about 3.3 seconds or so, the displacement is 0. What that basically means is the object is 0 meters away from its starting position, so it's actually at the starting position. Okay. I've highlighted the words values and position in blue. The reason I've done that is because it's important to make the distinction between the values here and the position that the object's in, and the changes in displacement and what they can tell you. So the change in displacement, whether it's changing and becoming more positive, so it's going in this direction, it's increasing, or it's becoming more negative and it's decreasing, will tell you the direction that it's moving in. So again, if we imagine that positive is to the right and negative is to the left, then the changes in displacement here, or here and here, will tell me whether it's moving to the right or to the left. So in this first case, between 0 and 1 seconds, the displacement is becoming more positive. It's increasing. Think of it as a number line if you want, and it's moving to the right in that number line. It's going 1, 2, 3 in that direction. Because of this, I can say that it's moving to the right. It's moving in a positive direction. In this section here, between 3 and 4 seconds, the numbers are becoming more negative. They're moving to the left in that number line, if you want to put it that way. And because of that, I can tell that the object is moving to the left. Okay, the directions on the number line and the direction it's moving in aren't related, but gives you a wee idea. So if it's moving in a positive direction here, because I've decided positive is to the right, then that means it's moving to the right. If it's moving in a negative direction, then because I've decided that negative is to the left, then it's moving to the left. Even though this bit up here, the displacement's positive, the movement, so the position is still to the right, but the movement here is actually to the left. Okay, so again, it might take you a wee while to kind of get your head around this. The next slide might help though a wee bit as well. But the values of displacement tell you the position, and the changes in displacement tell you the direction of movement. So following on from what we've done there, we've learnt that a displacement time graph shows the position of an object at any time. We've also learnt that if we look at the change in displacement, it tells us a little bit about the way that an object, the direction that an object is moving. Well, the gradient of a displacement time graph shows the rate that the displacement is changing each second. So if we actually get the gradient of this graph, it will tell us how much the displacement is increasing or decreasing each second. This is called the velocity. The velocity is equivalent to speed for a distance time graph. Tells us the rate that the displacement is changing each second. So if we want to calculate the velocity in the first second here, then we'd have to calculate the gradient of the graph. There'll be an example of this in the worked examples that are to come. Right, this is one of the worked examples that I'm going to give you here. I've got a series of worked examples that should take you through pretty much every possible example and every possible question that you're likely to be asked about these kind of graphs in physics. They cover pretty much every question that I've set for you in the Google Classroom. So I would suggest that as well as going through this one time, or maybe multiple times, to try and understand it, that you refer back to this when you get stuck. Okay, so the first example. What is the object's displacement after 2 seconds? Well, this one's relatively straightforward. If you go along to 2 seconds here, and you go up, and then you follow along to the side here to this y-axis, it will tell you the displacement. We're really just reading off the graph. So after 2 seconds, the displacement is simply 2 meters. The second example is to explain where the object is after 4 seconds in relation to its starter position. Now there's a couple of things that are important here. The first thing is the word explain. In physics, when we use the word explain, we're expecting you to give us an answer. So for instance, where is the object after 4 seconds? But we're also expecting a little bit more than that. We're expecting a little bit of explanation. How did you come to that conclusion? What evidence do you have? So let's go back to what's going on here. So after 4 seconds, we're looking for 4 seconds here. So we go along to the graph and we look at 4. And at 4, the graph is down at 0. Back at 0 seconds. That's our 0 meters. So that means that the displacement is 0 meters. So where is the object? Well, from what we said in the last little bit, the last slide, at 0 meters, it's back in its starting position. So we're going to explain this. We have to say that first of all, it's back in its starting position, but we need to say why. Why do we know this? Well, we know this because the displacement is 0. And really, when you get an explain question, saying a little bit extra is not going to do you any harm. What is the velocity of the object after 0.5 seconds? Well, 0.5 seconds is going to be around about here in the graph. And to get the velocity, again, if you go back to the previous slide, and this is where it's maybe useful if you make some notes as you're going along, because you can't remember all this at one time, no one could, then we need to get the gradient of the graph at this point. Now, to get the gradient of the graph at this point, really, because it's a straight line, we just need any 2 points in a straight line. So remember what I said before? To get the gradient of a graph, it's y2 minus y1 over x2 minus x1. Just to keep this a bit shorter, I'm not going to go through full details of how to do this, but the 2 points that I would look at would be 1, 2, my first coordinate, and 0, 0. You could be asked to draw a distance time graph that corresponds to a displacement time graph. If you do these, as I'm going to show you how to do them, step by step, and you follow the rules, then they're not too bad. Please don't try and jump to the final answer, because the final answer, especially when you're doing them at first, will not necessarily be obvious. It won't necessarily be intuitive. The rules you have to bear in mind here are, first of all, that distance always increases. You can't remove it. If you walk across the road from your house and then you walk back again, then your displacement is 0. It must be 0 because you're back to your starting point. However, there's no doubt about the fact that you've obviously covered some distance. You've walked out there and you've walked back. If you had a step counter on your wrist, then the step counter for every step you take is going to increase. You can't walk backwards and decrease them. Distance is basically the same thing. When you look at these graphs, or the displacement time graph that you're going to start off with, and I'm going to show you on my one here, we've got 3 sections here. 1, 2, and 3. So these 3 sections we're going to take a little bit at a time. We're going to take one at a time. We're going to work out the distance travelled in each section, and we're going to add it to the total distance. Once we've done that, we're going to, or for each section, we're going to plot the next section of the distance time graph. It'll become clear, hopefully, once I show you how it's done. So, for the first part here, when we're going from here to here, the displacement's increased by 2, and also the distance has increased by 2. It's moved 2 meters, let's assume it's to the right. The distance has basically increased by 2 as well. Fairly straightforward, it's not too bad. For the second section, between 1 and 3 seconds, the displacement hasn't increased at all. And that basically means that the distance hasn't increased. The object hasn't moved at all in this section. The tricky bit in this graph is possibly the last section. The last section, the object has moved from a displacement of 2 to a displacement of 0. Now that means that the displacement has actually decreased by 2, or the displacement has actually been in the opposite direction by 2 meters. But we're looking at distance here. Remember, distance does not go down, so it's a bit like walking across the road and coming back again. When you come back again, you're still covering the same distance as you did in the first part of the journey. So although the displacement comes down to 0 again, the distance here is 2 meters. So now we've got 3 distances. We've got a 2 meter between 0 and 1 second. It's increased by 2 meters between 0 and 1 second. It's increased by 0 meters between 1 and 3 seconds. And it's increased by 2 meters again between 3 and 4 seconds. Increasing every time. So now we need to plot our distance time graph. Okay, so showing you again the displacement time graph, and I'll add on the bits for the 3 sections. You notice I've just shown you the change in the displacement as well. This is just to give you a wee idea of what's going on. The bits we're interested in, though, are the changes in distance. Now, I've unfortunately got to show you the whole graph at one time, so this is kind of the answer. This is the distance time graph as it should look. Let's look through each section at a time, though. The first section, the distance and displacement have both increased by 2 meters in 1 second. So the first part of the graph is exactly the same. It's basically going from 0 to 2 meters like this. It's a steady increase. The second part of the graph is also the same. The distance increase here is 0 meters. Displacement and the distance both don't increase at all, so we've got a flat horizontal line here. The last part of the graph, though, is where you do see a difference. Going back to the displacement time graph for a wee second, S equals negative 2 meters, but D equals 2 meters. So instead of decreasing from 2 meters back down to 0, it's actually going to keep adding on. So it's adding on an extra 2 meters in this section. So that section, the first section, is exactly the same as the previous, as the displacement time graph, but the second section is not the same. It's different. In this bit, we're actually increasing by another 2 meters. Okay, the total distance totally increases. We're not interested in the direction. The next question that we could be asked is to draw a corresponding velocity time graph from a displacement time graph. Again, we're going to use the same sort of techniques as we did last time. We're going to do it section by section, and we're going to look at the velocity in each section. So we've actually already calculated velocity from displacement time graphs, so you may need to go back and have a look at that part of the video. And again, if you need to make notes about that, then make some notes and then come back to this. So to get to the velocity on a displacement time graph, what we're looking for is we're looking for the gradient. We're looking for the gradient of the graph. We calculated in question 3, a couple of slides ago, that the velocity in the first second from 0 to 1 seconds was 2 meters per second. That was the gradient of the graph in this part here. We can calculate the gradient for the other two sections in a similar way. I'm not going to do it here to save time, but what we'd find is that between 1 and 3 seconds, there's no gradient, the displacement isn't increasing, there's no velocity, the object isn't moving. And between 3 and 4 seconds, it's negative 2 meters per second squared. Just be careful when you're calculating the gradient. If it's sloping in this direction, it must be negative. So make sure you get your points the right way around. So once we've got this information, we can now transfer this onto our velocity time graph. So the velocity for the first second is 2 meters per second. Between 1 and 3, it's 0. And between 3 and 4, it's negative 2. Right, I think the sentence at the top of the page perhaps tells you a little bit. This is something that you might take a while to get your head around, but as long as you're logical and use the information that we got from the previous slide, so the velocities at different times, and you have a look at this graph here, hopefully this should make sense. However, this graph is not what I'd call intuitive. It's not obvious. You definitely have to do this section by section. You have to do this logically, because this is probably not what you would have written if I'd asked you just to guess what the graph might have looked like. It's important to remember that velocity is also a vector, so it has negative values as well as positive. And the other thing I think is probably worth pointing out about this graph is that these sections here, they can sometimes be done by dotted lines, reflect the fact the velocity is actually changing from 2 immediately to 0, and then immediately to negative 2. Now whether this would actually happen in practice is debatable, but from the data that we had and the graph we had in the previous section, this is the result. If you want to do these vertical lines and as dotted lines, that's kind of okay. Hi, hopefully this part is going to be a little bit easier. It's going back to something that you've covered at National 4 and National 5. What's the average speed? And again, this is why it's quite important to know the definitions. From Nat 5, or in fact Nat 4, the average speed is total distance divided by total time. Now, if you know these kind of definitions in this way, then it's actually easier to do some of these questions. It probably didn't really bother you too much the last couple of years, but if you've done Nat 5 before. But knowing that it's the total distance divided by total time will possibly make this a bit easier. Now, we've already calculated the total distance. If you look at your distance time graph, from question 4, the final distance was actually 4 meters. So we've got the total distance from that. The total time, well, we can get it from the graph here. The total time is basically 4 seconds. So 4 meters divided by 4 seconds gives you an average speed of 1 meter per second. I suppose you could be asked for the average velocity as well. Remember, the difference would be that the velocity would be the displacement divided by the time. Now the velocity, or the displacement, sorry, is 0. So therefore the average velocity is actually 0. Right, one last bit that I wanted to point out here. Negatives and positives. Is anything different if you have negative displacements? Well, not really. The fact is that when you have to do calculations with negative displacements, you just use the same rules as we've had above. I'm going to do one example though, because there is one area where I think it could be a little bit difficult, and it's going back to the distance time graph. So we're going to convert this to a distance time graph, and hopefully then you should be set to do the questions. So here's our displacement time graph from the previous slide. In the same way as we did before, we're going to split it up into 3 sections. The first section from 0 to 1 seconds, the second section from 1 to 3 seconds, and the third section from 3 to 4 seconds. For each section, we're going to look at the distance travelled. So the first 2 sections are very, very similar to the previous worked example. So the first section, the distance travelled is 2 meters. I've put a plus in front of it just to show that the distance is always increasing, but distances can't be anything other than positive. The second section also hopefully shouldn't pose any challenges. There's been no distance travelled. The third section, however, is maybe slightly different, so it's possibly worth just mentioning very briefly. Okay, so the displacement here at 3 seconds is 2 meters. And the displacement at 4 seconds is minus 1 meter. What does that mean? Well, if you imagine that 2 meters, this is plus 2 meters, this is an object starting 2 meters to the right of you. And it's finishing 1 meter to the left of you. So the distance travelled here is 3 meters. Really, it's the difference between 2 and negative 1. So at this point now, we can use the same process as we did before to change it into the distance time graph. In the corresponding distance time graph, in the first second, the distance is going to increase by 1 meter, by 2 meters. The second section, between 1 and 3 seconds, the distance doesn't increase at all. And then the last section, it's going to increase by 3 meters. It doesn't really matter to us anything else to do with it crossing the axis here. It doesn't actually matter at all. It's really just the difference in displacements. How much has it moved up and down in this direction, I suppose. Again, if you do this logically, it's not too bad. It's when you try to do it on the hoof as such, and you try to work it out straight away, then that it can become significantly challenging. Okay, at this point, I would say now try the questions. I think the bit of advice there about referring back to these slides is something you're going to have to do quite a lot. That's okay. That's part of the challenge of higher physics, but it's also actually something that will allow you to hopefully understand it. And again, previous advice about using other resources, Scholar, about asking lots and lots and lots and lots of questions in Google Classroom, it still stands. Please make sure you do. Okay, good luck, and off you go.